In week 7, we study linear regression. And the majority of the work is done in StatCrunch. However, some people want to know what's really going on. And that's what this video is going to be about. So let me first remind you what it meant to be a deviation. A deviation of some data point was just how far it was from where we expected it to be. It's deviation. So if that data point has this name, then its deviation is observed minus the mean. So I have this deviation, and we built the standard deviation in 2 steps. We said that the standard deviation, so at the end of it all, we said that the standard deviation was equal to the square root of the variance. And we defined the variance. We defined the variance to be equal to the sum of all of these deviations. I would take all these deviations. So this is the deviation for the first data point, and this is the deviation for the second data point, and so on. I'd have a bunch of deviations, one for each data point, and we squared all of those deviations and then divided by n-1. And if I take the square root of the variance, then this would be the standard deviation. But now I want to define something a little different from the variance. This here would be the sample variance, right? Because the mean we're using is x bar, so this is the square root of the sample variance is the standard deviation s. It's the sample standard deviation. But now I want to deal with not just with one data set. Well, it's still one data set. So this is what our data set looked like just a moment ago in that definition of standard deviation. But now I want to deal with pairwise data, right? Like, for example, this might be a list of people's heights. This might be a list of heights. But now I want to pair up someone's height with their shoe size, let's say. And so the y values here can be someone's shoe size. So I would end up with these ordered pairs of data. You have pairwise data, you would say. And maybe this is my data set. So each point in the data set would be like a point in the XY plane. It's an ordered pair. So then not only would I be having this list of heights, or this data set of heights, but I'd also be having the shoe sizes as well. And it could form this, well, it absolutely would have this, it would be this pairwise set of data, and I could extract from that just this collection of the shoe sizes. Then we can define something called the sample covariance. It's not the sample variance, it's the sample covariance. And it would be, you know, of x and y. It's the sample covariance of x and y. We will denote it as COV of x comma y. And it's very familiar to us because we know how we built the variance. When we were building the variance, we took all those deviations of x so there's one of the deviations for the first data point, and then there it is for the second data point, and so on. And we went through and squared them, right? But if I squared it, then that would just mean that I would have another one here, wouldn't it? But instead of me having the x information here and it being squared, I'll put the y information. So this would be y1 minus y bar. And then we'd have, for the next data point, normally you'd square it, there'd just be another one multiplied, but now because it's the covariance, we'll make it be for the y data. And that's what our numerator looks like. The denominator is still n minus 1. And we call this the covariance. So it's just like the variance, with the exception of, instead of the numerators being looking like this, you still have two terms being multiplied together, but now the other one has just got the y information. Okay. So if this is our definition of covariance, then let us define another term called the correlation coefficient. The correlation coefficient, which is denoted as a little lowercase r, it's an r. Too often I'll see people trying to write it like it's a square root symbol. No, it's a maybe my little lowercase r is silly looking. I don't know how to make it look. Say lowercase r. This correlation coefficient, which is denoted as r, is the covariance of x and y divided by...
Sorry, I'm not sure about that.
Oh, hush. That's my Alexa. So it's the covariance of x and y divided by the sample standard deviation in the x direction and times the sample standard deviation in the y direction. You just take the x data, find its sample standard deviation. You take the y data, you find its sample standard deviation. You multiply them together. That's the denominator. This is r. This is that number that StatCrunch is computing for us automatically. Okay. And since the numerator, well, that's good enough. So this is r. And recall that r lives between -1 and 1. Where if it was equal to 1, it would be a perfect positive correlation, and all of those pairwise data would be right on some line if it was equal to 1. And if it was exactly equal to -1, it would be perfectly negative correlated, and all those data points would be right on some line with a negative slope. This is where that value of r, this is how it's computed. Okay. We can now define what it means to be the linear regression line. So the linear regression line I'm doing all this so you'll appreciate the automation that you get from StatCrunch. The linear regression line is it's this y hat, and for whatever reason in statistics we always put it as b plus mx. We don't write mx plus b. And if that's our line, and we're calling it y hat, and it has this y coordinate for the y-intercept, and it has this slope, how do we get that slope and y-intercept? Well, the slope would come from the covariance of x and y divided by the standard deviation, the sample standard deviation in the x direction squared. That's our slope. And the y coordinate of the y-intercept, the b, satisfies that y bar minus m times x bar is b. And this right here is telling you that it must be the case that it must be the case then that the point x bar comma y bar is on your linear regression line. It must be, since it satisfies, since this is how b is computed. So this point is on the line. And we could go one step further and say that the equation of our line then would be just y hat minus y bar equal to m times x minus x bar. And then you don't have to worry about writing a separate value for b. Or I guess I could move this y bar to the other side for you. The equation of your line is y bar plus m times x minus x bar. Now look at how that line, look at how this formulation of it jibes with this idea. If x were taken to be x bar, then that would be x bar right there, and it would say x bar minus x bar, which is 0. And if that's 0, then it's gone. And so you'd have that your line goes through your line has the y coordinate of y bar when x is x bar. And this is the formulas for linear regression. So this would be the data from example, or from question 2 on the homework. Let's do it as an example. I just opened the data in StatCrunch because I'm going to want to compute the covariance. So I can go to summary stats, covariance, and tell it the columns and compute. So I get a covariance of those two columns, minus 27 point yada yada yada. So it would be minus 27.659091. There's my covariance. And I'm also going to want my sample standard deviation of each of those columns. So I'll just select them both then the sample standard deviation for the first column is 13.405958, and the sample standard deviation for the second column, the y values, 7.6053211. All right, super. So then my R value, since it is the covariance of x and y divided by sample standard deviation in the x direction times the sample standard deviation in the y direction, would be minus 27.659091 divided by the product of 13.405958 and 7.6053211. And if I use my handheld calculator, I get an R value of negative 0.27128, and so on. So there's a negative correlation, but it's not very strong, right? Because if the R value is close to 0, then the correlation is very weak. And now I can construct my best fit line. I will get the slope. The slope is just the covariance of x and y over the standard deviation in the x direction squared. Well, that standard deviation in the x direction was 13.405958. We would square it, and my covariance was minus 27.659091. Okay, so when I use my handheld calculator, I get a slope of minus 0.1539. And for me to compute my y-intercept, I would need to know x bar and y bar. Okay, so come back over here. X bar is this and y bar is here. So what? So this would be y bar minus mx bar, and y bar was 44.75, and m being a negative 0.1539, and then times x bar, which is 38.916667. I can compute that y-intercept with my little handheld calculator to be 50.739. And we'll do one more digit. All right, so then y hat should be 50.7397 minus 0.1539x. Well, then if I was inclined to, I could use this line to make predictions about the correlation between the numbers in that data set that we were looking at. Let's look at a, so we'll just do the regression. We'll go to stat, regression, simple linear, and this was our x variable and this was our y variable, and when I hit compute, you get the 2-page summary. And let's check our, let's check everything. So the correlation coefficient minus 0.271, that's what we got over here, minus 0.27128. And the equation of the line, you would read that as y hat is equal to b minus mx. And so 50.739. So I have 50.7397. And so we only differ just right there. Of course, I just copied it down wrong. That's the problem. It's really 50.7393. And so we are in a perfect agreement because that's what they have, 50.7393. And then I kept 4 digits here, minus 0.1539. And that is exactly what I have right here and there. And that's how it's done.